Welcome to Web Handling. My name is Dave Roysam. I am super excited to start a new mini-series on machine speed concerns. In this introductory clip, we will show that what you do with speed information informs you as to the required resolution and response of your speed sensor. Sensors include encoders, tachometers, strobe lights, laser Doppler Anemometry, and more. Design examples are given for more demanding applications. I know your time is precious, so let's get started. Let's begin by describing what our sensor readouts are being used for, whether they be for speed or anything else. Simply saying the information might be useful or that we've always measured it like this is far, far from good enough. Instead, perhaps the operator or process engineer might use the information to make process setting adjustments. QA might use it to reject products. Troubleshooters may use it to determine possible cause and effect relationships. The end use determines how good the measurement needs to be in terms of accuracy and resolution and response. If we now turn from sensors in general to speed sensors in particular, we can list some common applications. This will inform us to the required resolution in, say, parts per thousand, as well as required response in hertz or readouts per second. Using speed to assess productivity, such as tons per day, or product length, say meters per roll, is not so demanding. Either will need to only be accurate to say about 1 part in 100, and response will not need to be particularly fast. Master speed will also not need to be super accurate, but does need to be quite a bit faster, say 1% and 100 hertz respectively for an ordinary machine. However, when we get to various components of tension control, sensor requirements can easily be an order of magnitude or more demanding, particularly in terms of resolution for any form of speed differential, sometimes inappropriately called draw control. Soon we will show that you might need to be able to resolve better than 1 part in 10,000. And to do so at response rates greater than 100 updates per second. Motor tachs are one of the most common and most accurate ways to get a speed readout. We will list others shortly. In this case, and also for some other methods, we may only need to know 3 things. A unit conversion factor that may include a gearbox ratio, the effective radius of the roller, and the rotational speed of the motor. In this clip, we will size resolution and update frequency as a way to inform us as to the required encoder counts as well as counter speeds. Next week, we will discuss why roller radius may not be so simple, as well as other complexities. It is often prudent to size components for worst case. While you might sometimes pay a bit more for the sensor, you might, in compensation, not have to engineer a new sensor for the next machine and stock spare parts for both. We covered this calculation in Web20177a, so you can review the details there if you wish. In summary, a worst-case sizing requires our sensor to resolve 1 part in 10,000. That means that both roller RPM and roller diameter have to be that good. So, let's size our worst-case RPM sensor, whether it be an encoder, resolver, or tach. The worst case from the last slide is 1 part per 10,000. Here we add a response rate of 100 readings per second, corresponding to a rather ordinary scan rate of a PLC or drive of 10 milliseconds. Given those parameters, we find that the encoder counts should be more than 1 million per revolution. For a point of perspective, a 22-bit encoder is running at 4 million counts, and a 24-bit encoders are commercially available. If you have a 1200 RPM motor, the counter needs not to choke at pulses coming in at 20 megahertz. Again, high, but not out of the ordinary for commercial sensors. So now we can evaluate some options for speed measurement against our two criteria, resolution and response. All but one of these methods here can, on occasion, meet our requirements. The exception is the handheld Tach, which fails both resolution and response criteria for almost all applications. We will see more about the handheld Tach's shortcomings in next week's show. Let me finish with a lesser-known speed measurement, but one that I find quite interesting. That is, any roller or shaft that has a target on it. That target could be optical or metal or something else. Even so, the criteria will be the same. That is, how sharp does the target need to be and how narrow does the sensor window need to be? If you want to think about the sharpness of a target, consider a ragged piece of tape or a fat, fuzzy line made with a magic marker. Similar ideas hold for the sensor. A fat sensing window has a large uncertainty compared with a tiny slot. In any case, let us use a more moderate resolution of 1 part in 1,000 and apply that to a 10 centimeter radius roller. A quick calculation will show that the target and sensor needs to be sharper than about 5 hairs thicknesses. Tight, but by no means unusually so, as many commercial sensors can do that. Of course, that is the required resolution for an update of once per revolution. If you allow averaging and updates to occur over 10 revolutions, the sharpness could be a ragged piece of tape or a fuzzy magic marker line. I hope you've enjoyed this introduction to speed measurements. Stay tuned for next week's show, where we will show that there are other design complexities that must be considered to deliver a trustworthy speed measurement. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. See you next time.